Okay, there we go. So I'm now recording my screen. All right, so we're going to work with carbonate. We're going to use the equilibrium constants for carbonate. I'm going to paste these into my speciation diagram so that I can calculate the alpha 0, alpha 1, alpha 2 for this species. And here's my plot. pH on the x-axis. The first pK was around 6. The second pK was around 10. Notice I've got all of my alphas because I made it generic, but only the first 3 actually matter in this case. The red one is the acid form. It starts at 100% and it goes down. The green one is bicarbonate. It starts very small and it goes up to 100%, halfway between the 2 pKa's, and it goes down. And then the third one's the one we care about in this case. It's the carbonate speciation or fraction, and it goes from a very small number, it's not 0, right? It's a known number, all the way up to close to 1. Okay. So if you do the solubility calculation out at pH 14, this is completely right. Right? Because all of the carbonate in all of its forms is just carbonate. And if you did this at pH 1, it'd be completely wrong, right? But if you did it at pH 14, you'd be completely right because the alpha is 1. All right. So we want to do it at actually any pH. So we're going to go ahead and fix that. We're going to be able to calculate this at any pH. So the first thing I'm going to do is a highly technical maneuver to create some space. All right? And I'm going to calculate KSP prime as a function of pH. And so I need to know the KSP, and it's equal to 4.5 times 10 to the minus 9. Okay, so I put that in as a constant. And now KSP prime is equal to that. I'm using apple T. That's what I'm doing here. All right, it's $L, $11. I used Apple Control or Apple T to do that. You can put it in by hand. That way, when I fill down, that number doesn't move. And I'm going to divide it by cell what? I need that, right? Where do I get that? I don't have any alphas in here, but I got A's. That looks like cell. I'm doing this row. Boom. Right there. Okay. Is there carbonate in this system at pH 0? Yes. 2 times 10 to the minus 17, right? It's really small. It's not 0, but it's small. So I'm going to click on that cell. So I'm going to just click on F2. And I'll hit return. Okay. That calculates my KSP. Remember we said if KSPs are big, it's really soluble? I don't know, that's kind of big, right? Ridiculously big, right? I mean, there's no way. You'd have to dissolve the entire Earth to get that amount. I mean, that's a lot. That's an exaggeration. You'd have to dissolve the state of Maine to get that amount of stuff, right? It's huge. So now I want to fill it down. I want to do this calculation for every pH. So, Excel trick. Click on your cell. See that little green corner box? See if I better pay attention. Boom. I just double clicked on it. Boom. All the way down. And if I scroll to the bottom, where the pH is 14, guess what the KSP is? 4.5 times 10 to the 9. Why? Because the alpha became 1. Okay. So that's good. That's my first step. We're going to go lose all this stuff. Clear. Those are gone. Good. Let's calculate Z. What is Z? It's the square root of the KSP prime. I know the KSP prime, so let's just take the square root. Two ways to calculate the square root. One is you can just type in SQRT, and I get the square root, and that worked. Or you could raise it to the 1/2, right? Take the exponent to the 1/2 is the same thing as doing the square root. That's going to be important if you want to take the cube root of something, because there's no cube root function in Excel. So if you want to take the cube root of z, you would raise it to the 0.3333, and if you want the 4th root, you'd raise it to 0.25, etc. So that's just a Excel trick. Double click on the back corner, and that's the solubility. We're done at any pH. And so now let's plot it. So let's call this calcium 2, and I'll highlight it. And I'll do apple C to copy it. There's no chemistry here. This is just Excel eye candy. I click on the graph I want to put it on, and I do paste, Command V, and it's on there. And then I'm going to lose this degree of proteolysis line. And there it is. Starts super small, 6.7 times 10 to the minus 5, and it goes shooting up to like 6 molar, and then it goes off the scale. This is not very satisfying as an intuitive thing. So fine, we'll relabel it. Make that calcium 2. It's completely correct. It's just not satisfying because it changed over like 15 orders of magnitude. Let me drag that there. So what I'm going to do is click on this y-axis, and I'm going to tell it, plot that on a logarithmic scale. Okay? And I'm done. So now you come in, it's on a logarithmic scale. Oh, the cool thing is, pick your cursor, stick it on there. At pH 13, what's the solubility? 6.7 times 10 to the minus 5. Exactly. But at pH 8, it's decreased by almost several orders of magnitude. That's going to be 9, 1, 2, 3, 4. Looks like 9 times 10 to the minus 4. And if I get up to something like typical of acid rain, which is up here, say at pH 5, now my carbonate concentration is 0.15, right? That's more calcium than seawater. So what does that say? Rocks dissolve at pH 5. And they're going to keep dissolving because what's going to happen is you'll never have enough calcium and carbonate to come to equilibrium. It'll just dissolve. You'll run out of solid before you can get to this concentration. So this is an entirely correct, mostly correct, we'll have to fix a few things next class, calculation. So let's think about what we did. We took the degree of proteolysis, these alphas, we used it to compute the side reaction. We recognized that this solubility is a function of that side reaction, so we calculated a conditional KSP here. And then once we had the conditional KSP, we could just do our solubility problem, and we're done. Okay. So, and now you can do any pH you want. And you can, so this is now in your toolkit. So the Intergovernmental Panel on Climate Change has a really cool graph, and they show you how the carbonate chemistry changes as the Earth gets acidified. And what they're basically doing is they're looking at the differences in these numbers as we go from pH 8.2 to pH 8.1 to pH 8, etc. And they're also doing a little more sophisticated calculation. They're including all the other things, all the other acid-base chemistry that would go on. Okay, questions?